Hello. In the previous lecture, we talked about address translation regarding virtual memory and what a page table is, how it looks. Then we saw how the page table is being used for address translation, and we ended the lecture with the note that if we have to access page table every time there is a memory access, then it will be cumbersome and it is not efficient, right? Because for every address, for every memory access, we need an additional memory read, so it takes a lot of time. So to avoid that, we use something similar to a mechanism, something similar to a cache called as the translation look-aside buffer. So what in translation look-aside buffer, typically there will be 16 to 512 entries. It is not such a big memory. It is a small memory having a maximum of something in the range of 16 to 512 entries only. But again, it is assumed or not assumed, it is want to give around 99% of hit rate, which is excellent, right? So here also we like similar to cache, here also we are exploiting the concept of spatial locality and temporal locality. Now let's see how this cache, this translation look-aside buffer is implemented. Okay, so here we are. Let's do with an example. Consider the virtual memory of figure 821. I hope you remember. Use a 2-entry translation look-aside buffer to translate this and this, right? 0x247c and 0x5fbo to physical address. And suppose the TLB currently holds valid translations of virtual pages 0x and 0x 0x2 and 0x7ffd. Now let's see how it looks. So this is very much similar to a fully associative cache. There is no concept of set here, so that for any location, any page virtual page number can be, and the corresponding physical page number can be stored in any location. So this is something having only 2 locations, right? So how does it look? We have the virtual page number 0x00002 and the virtual page number 0x7ffd. So these are the 2 entries that are there, and their corresponding physical page number also. So the physical page number corresponding to the virtual page number 0x7ffd is 0x0000, and the physical page number corresponding to the virtual page number 0x00002 is 0x7fff. So these 2 entries are there. So when the processor requests requests a virtual address of 0x0002473, this is a full virtual address being requested. Then what is it done? Then the page number is searched. The virtual page number is searched, right? So it looks in the entry here. Okay, if whether this is there, a comparator is used to compare the virtual page numbers, whether this is there, no, or this is there. So if there is a hit, this is a 1, okay, fine, there is a hit, right? There is a hit here, but one more thing is the valid bit should be 1, right? The contents of these 2 should be valid, so this valid bit is also considered. So the comparator's result and the valid bit, or what, the hit. So with this we consider the physical page number and we map it into the physical address, and the page offset is directly taken here, and we have the final physical address, right? So suppose this is a 2 entry translation look aside buffer. So what if it was a 4 entry? Then 4 more valid bit virtual page number and physical page number locations would have been there. If it was a 16, then like that 16, and for each of these there should be a comparator and the multiplexer will be that big. So this is a expensive thing to implement, translation look aside buffer. So much hardware is required, so it is that is why it is being restricted to 16 to 512 entries only, and even then we are getting a very good hit rate, satisfactory hit rate we are getting. Okay, now moving on to our last topic in virtual memory. It is called as memory protection, right? Till now we were just talking about one process, single process or a single program, right? But in a real computing system, multiple processes will be running at the same time, and most of these processors will be having some sort of memory access. So there is a chance of clash, right? There is a chance of multiple processes being or multiple processors accessing the same physical memory. So even though this concept of virtual memory is developed to it is developed to give programs or processes more the sense of having more memory. This memory protection is also key, or it is an important idea for implementing or reason for implementing virtual memory. So what happens is that when we have the way we are implementing virtual memory, even though each process is having a certain size of virtual memory, it is mapped to a limited area in the physical memory, right? Because no matter how big or how many number of pages or memory locations are there in the virtual memory, in the physical memory we are not using all of the physical memory, we are only using a certain number of locations, and the remaining we are managing with the hard disk. And if there is a if there is a page fault, we replace the current thing. So with this concept we can actually ensure memory protection. That is, we do this address translation in such a way that there is no clash between the memory or physical memory locations allotted to the separate processes. Also, the other thing is that this can be used to for sharing actual data also, right? So this virtual memory, this address translation can be used to isolate processes. That is, it can be used to make sure that say process A won't take the data that is used by process B in the physical memory. Also, if process A and B wants to share some data, that also can be arranged by mapping the corresponding virtual memory locations to the same physical memory. That also can be done. So this segregation of memory for the memory protection is also one of the key component of virtual memory, right? So and one more thing, we talked about page fault. So what is page fault? Page fault occurs when the data that is being searched for or the page that is being searched for is not in the main memory, and that is in the disk. Then what happens? Then what happened when the process in cache? What happened when the processor looked for some data in the cache and it was not there? Then that corresponding data was or block was taken from the main memory and put into the cache memory. And if there was some if the cache was full or the corresponding set was full, then what happened? We use some replacement algorithm to remove evict one particular block and put the new block in place. Similarly, here also, if there is a page fault, what we do is we go to the main memory, we go to the hard disk, take the corresponding data, and we put it into the main memory in the physical memory according to the page table, and we update the page table, right? And also if there is some requirement for if there is a condition occurs that the physical addresses or the physical locations allotted for a certain process is full, and some new page is being taken from the hard disk and put into the main memory. Similar to cache memory, some replacement algorithm is used to evict some page and the new page is put into place. So that is also there, that is page fault, and replacement algorithms for pages. So with this I am ending the lectures on virtual memory. And so I am winding up the session on virtual memory, and this whole process of taking like managing the data between the memory space between physical memory and this hard disk, and taking pages from the hard disk and putting it into the memory, and like that, vice versa. This whole process is called as paging. Okay, I forgot to mention it in the beginning of the lecture. It is called as the whole concept is called as paging. So that is it. I'm winding up the lectures, and with this I think the whole portions for our computer organization syllabus is over. Thank you.